Okay, then we do it at the end of the lecture.
Yeah, thank you very much.
Yeah, I think you see now my shared screen, right? Mm-hmm. Okay, so I will talk today about nitrate. Nitrate is a major problem all over the world, I would say, and also especially in Europe. And I would like to talk a little bit about the background. Why do we have this problem here, and maybe also what can we do about it? Well, there's not so much we can do about it, but there are things that we can do. So the nitrate problem, what happens in the underground? And I start this lecture with this slide, which is in a way a very interesting one. This is the so-called EU Water Framework Directive. This is the legal document by the European Union, and all member states are actually bound to this document. The Water Framework Directive, maybe you heard that word before, was implemented in the year 2000. Yeah? And what it states, the first thing it states, and I find this a very important statement, water is not a common good, but an inherited asset that has to be protected, defended, and treated accordingly. And this is right now discussed in the EU a lot. There is some states that have privatized their water companies, and Germany hasn't done that. They did that some years ago, but actually they bought it back into public companies, and we don't have private water companies, which are basically the ultimate goal is making money. And we have other countries where this is different. But this is what the EU Water Framework Directive says. Water is not a common good, but an inherited asset that has to be protected, defended, and treated accordingly. And this is actually true, in my opinion, and we have to act like this. The second thing in this Water Framework Directive is this. And this is also a statement that was done in 2000. Yeah? And this was also valid for all member states. And what it says here in that statement is that until 2015, for every groundwater body, a good status in terms of quantity and quality has to be reached. Yeah? This is a major announcement from the European Union. And I would stress again the fact that it was implemented in the year 2000, and 2015 was the deadline. And what they told the member state is, until 2015, you have to reach first good quantitative and chemical status. They already, in a way, acknowledged that that might not be happening that quickly. So what they also then offered as a way out, you could show the reversal of contamination trends. Also, this was something they said, okay, if you're not achieving good status, at least you should show that you have a reversal in contamination trends. And there were two other measures: prevent contaminant input or limited input, and prevent deterioration of quality. This was the statements in our Water Framework Directive. Binding for all member states. Yeah? Every member state in the European Union agreed on this. The next slide shows you this now. And this, I remember, you remember maybe this was 2015. Until the 2015, we should have achieved a good quantitative and chemical status of our groundwater resources. Then you see that Brussels, April 2016, Water Commission refers Germany to the Court of Justice of the EU over water pollution caused by nitrates. Yeah? So 2015, we could not achieve the goals of the European Union, so they brought Germany to court. Yeah. That was a very interesting thing. The reason for the nitrate problem is this, actually. This is part of the reason. It's fertilizers in agriculture. Yeah. And this is one of the fertilizers, of course, that is used. Yeah. This is basically done mainly in the northern part of Germany, also in the southern part of Germany, of course, but this is basically the background. 2016, we were sued by the European Union. EU sues Germany over water tainted by nitrate fertilizers. EU takes Germany to court over high nitrate levels. EU sues Germany over environmental standards. So this was a major thing also here in Germany, and people were really concerned about this one. And now we continue, 2016, now we go to 2018, and this is in German, but this means Germany was convicted due to high nitrate concentrations in groundwater. And this is also 2018 here. And here it says Germany faces billions in fines for breaking EU laws on nitrate pollution. Very interesting, isn't it? This was a major story, of course, in Germany. They announced that we have to pay about 1 million euros per day. Yeah, roughly. I think 900,000 euros per day was the fine that we have to pay. After this, there were still negotiations with Germany, between Germany and the EU, and I think, I'm not 100% up to date here, I think we are still not paying. So Germany promised to do more than they did, and I think we are not paying right now. But these are really strong cases. The European Union brought Germany to court, and this is something I really would like to stress. There's EU laws on water quality, we broke it. Yeah. How can the European Union say that we broke the law? And this is also interesting because what we have in every member state of the European Union, we have a nitrate monitoring network. Yeah? And in Germany, we have about 700 monitoring wells where we measure, out of many parameters, one parameter is nitrate. And this network is specifically for nitrate. And the data which are generated here all over Germany are reported to the European Union in Brussels. And the European Union looks at these data and then they decide, did we do enough or didn't we do enough? Yeah? Did we reverse trends, for example, or didn't we do that? Actually, what I told you is 2000 it was implemented, 2015 was the deadline, and then we were sued in 2016. And the reason why we got sued is this. I think I showed this yesterday also. These are the percentages of observation wells in groundwater exceeding the legal limit for nitrate. Yeah? And the legal limit is 50 milligrams per liter. Yeah? And these percentages come from this network. Yeah? So all the data are analyzed, and then they found that from 2008 to 2018, actually 2015, the decision to sue us were made. They found that we are having always about the same number of wells with high nitrate concentrations. So you don't have to go to zero, of course, this is our target in a way, but at least we should have shown that there is a trend that we have less contaminated wells. We couldn't show that, so we were sued, and this is perfectly correct that they sued us. There was actually no indication. Yeah, so this is the background of the nitrate problem in Germany in terms of the legal aspects for that. So, reversal of contamination trends. We were not able to show that in the case of nitrate, and this is why we got sued. Yeah, and I think we not pay, we promised more. The EU also realized this was kind of ambitious to reach these goals by 2015. So they extended this deadline now to 2027. And this is the final deadline for meeting the objectives. If you look at this again, 2027 is just a few more years. I'm not very optimistic that by 2027 we will reach these goals that we have, and then there will be more discussion on what to do about it. And what is the problem here? And this is a map also of Europe showing us the problem. And what they plot here is the so-called nitrogen surplus, yeah, in kilograms per hectare. Yeah. And the nitrogen surplus is the difference between agricultural nitrogen input, so what we put on our fields in terms of fertilizers, and the output, which is meat, milk, agricultural products, whatever you want. Yeah, this is what comes out of agriculture. Yeah, we put nitrogen fertilizers in. We have the fruits, we have the milk, we have the meat, we have all these agricultural products that gets out of the fields again, and then we have a surplus. And this is the scale of the surplus, ranging from less than 10 kilograms per hectare to more than 150 kilograms per hectare. And what you see is that, of course, Germany here, the Netherlands, Belgium, also northern parts of France, Italy, this part here, and Italy here, Czechia and Poland, all these countries, they have a problem with too much fertilizers on their fields, and this is the so-called surplus. Yeah? The surplus is important because this is the nitrogen that you find in an agricultural soil after the growing season and before the next growing season. Yeah. So if you put fertilizer on the fields, then the plants take up these fertilizers, mainly nitrogen containing fertilizers. And then in the end of the growing season, there is still some nitrogen left in the soil. And this is the so-called surplus. Yeah. If I go to the next slide, I show you here that the surplus of nitrogen that we have in the soils after the growing season actually was increasing from the 50s. Yeah? And today we have a surplus in Germany, which is on average about 110 kilograms per hectare. Our target, that is what we would like to achieve, is 70 kilograms per hectare. Yeah? And we think we are still above 100 kilograms per hectare of surplus. This is not up to date, it goes just up to 2005, but not much changed. There's a lot of money spent to consult farmers, tell them how to put fertilizers on the fields, how to monitor that basically to get these numbers down. But as we saw before, we are not very successful in this, at least in what our monitoring stations show us for the groundwater. I will tell you later that also there is a problem with that. So how is the surplus of nitrogen in the soils, how is that determined? And this is pretty simple. In the end of the growing season or before the new growing season, you go to your fields and you take samples of the soil from different depths. You see that here, 0 to 30, 30 to 60, 60 to 90. These are samples which are taken here from the soils. And then you measure basically the N content, the nitrogen content in that soil. And then you can summarize what is the surplus we still have in the soil before the new growing season. These values should guide the farmers to put the appropriate amount of new fertilizer on the soil, because there is still something in the soil and they should then not do as much fertilizer as they want, but they should do that according to what is already in the field. However, there's another point. In the next slide, I first would like to show you how this nitrogen excess developed over time in Germany. And this goes from 1990 to 2017. Yeah? And 2017 means this is later than the end of the time period that was defined in the Water Framework Directive. So it was 2015. And also here you see that we have a kind of decrease in the nitrogen excess, the surplus in our agricultural fields over time. But over the last years, actually there was not much that happened. Yeah? It was very, very similar over the last years. Again, this is the target. 70 kilograms per hectare. This is what they would like us to have. The idea here is also, if you have a surplus in the end of the growing season, in principle, this surplus of nitrogen is a risk for our groundwater resources. Because in the end of the growing season, we are going to autumn to winter, so there's more precipitation, and in principle, this 70 kilograms of surplus could be flushed down to the groundwater, yeah? And then we would have nitrate concentrations in the groundwater. And the 70 kilogram was defined, this is the maximum we should have. Yeah? However, what you can do, okay, I'll come back to that point in a second, to the 70 kilogram. And this is the current situation now in Germany. 27% of all groundwater bodies are in poor chemical state due to these high nitrate concentrations. And here you see the map. This is the northern part of Germany, where we have a really bad situation that is mainly due to cattle breeding. Cattle is here the main agricultural thing. And this is the area where I come from here. This is the Darmstadt and Frankfurt are somewhere here. This is Wiesbaden and Mainz. Darmstadt and Frankfurt are here. And this is the so-called Hessian Ried. I told you a little bit about the Hessian Ried already yesterday, and we will go back to that Hessian Ried because it's such an interesting case study. Yeah, and here you see the state of Hesse. This is where I live. Here is Darmstadt. Yeah, here is Frankfurt. And this is the area I'm talking about today, the Hessian Ried. The red color shows us that we have here very poor chemical state of our groundwater, and this is due to nitrate. Yeah? And in Hesse, we have 127 groundwater bodies overall, and 25 are in a very poor chemical state. 19 of these due to nitrate. Hotspot, Hessian Ried. We have to say, and this is why we got sued, there was already in the year 1991 a nitrate guidance from the European Union. Yeah? So 28 years later, we still have a problem here. More than 20 years of countermeasures have been taken also to deal with the problem of nitrate. And 19 years after the Water Framework Directive was implemented, that was in the year 2000. I should write here now 20 or 21 years. Yeah? And this is why we got sued. This is the Hessian Ried. If you look into Germany, this is where I come from. This is the southern part of the state of Hesse. This is the state of Hesse. This is the Hessian Ried. And you see that basically everything here is red, meaning that the groundwater resources here are too high in nitrate. Yeah? And this is the problem we have. Yeah? The problem is that the Hessian Ried, 33% of that area in the Hessian Ried is intensively used for agriculture. Yeah? And that is also what causes these high nitrate concentrations. Farmers here are very frustrated because they do their best, and I believe that they do their best to not put that much fertilizer on their grounds, but still the situation is not improving, and the farmers get blamed for this. I will tell you later that this is not necessarily the fault of the farmers. There might be other reasons why we still have these nitrate problems. The Hessian Ried, in terms of geology, this is a kind of cross-section. So the Hessian Ried is a part of the so-called Upper Rhine Valley. Yeah? And there we have very thick quaternary sediment fillings, and these sediment fillings make a very good aquifer. Yeah? And you see here that we have basically the thickness of this quaternary in that here, this is the so-called Heidelberger Loch, goes up to 200-300 meters. Here's Darmstadt, and also here the sediments have a thickness of 100-150 meters, something like this. Yeah? And this is, and I told you about that yesterday, I will briefly show you that again. This is also where the water, the drinking water for Frankfurt comes from. Yeah? So we have conflicts here. We have agriculture, and we have production of water for drinking water purposes for the city of Frankfurt. Yeah, that is the point. And we have that situation. Everything is red because of the nitrate. What they do in the Hessian Ried, you see on these pictures here. The agriculture here is not cattle breeding, something like this. The agriculture here is more that you have vegetables. Yeah, this is a picture from the Hessian Ried. You have fruits. You have here strawberries, basically. And one of the major crops in the Hessian Ried is asparagus here. This is our asparagus field, basically. And to some extent, also it's a dry area, and we have to irrigate. Yeah? This is the irrigation system they have there. And again, these berries and the vegetables, they are growing here, the asparagus, they need kind of a substantial amount of fertilizers. And this is basically the starting for the problem we have. This is what I showed you yesterday already. I just wanted to remind you on this, that the Hessian Ried here, we are talking about this now, delivers 50% of the drinking water for Frankfurt. Yeah, that is the point. And therefore, we have a huge conflict here between the agriculture and the water producers that they produce the waters here. I showed you this yesterday. We have Mar also there. I don't want to go into detail again. I want to go back to the nitrate here. I told you some slides before that the target of our government is that we should have not more nitrogen excess than 70 kilogram per hectare by the end of the growing season. Yeah, this is our target. Yeah. However, if you have in the end of the growing season 70 kilograms of nitrogen per hectare still in the ground, potentially this can be flushed to the groundwater if there is no rainfall coming and we don't have crops taking out that nitrogen. It potentially can be flushed down to the aquifer. And we made an exercise here and we calculated if all these 70 kilograms of nitrogen are flushed down to the aquifer during the winter months, what would be the resulting concentrations in the groundwater? How can you calculate that? how can these 70 kilograms being flushed down to the aquifer? You need to consider groundwater recharge. Yeah, you have precipitation, part of the precipitation evaporates again, part of the precipitation generates groundwater recharge, and if you put all these 70 kilograms per hectare into the groundwater recharge, then you can calculate the concentrations that we will have at the groundwater table. So we did that for the Hessian Ried. This is a map from the Hessian Ried, and this map shows groundwater recharge. Yeah, how much is groundwater recharge here in the Hessian Ried? This actually is the River Rhine here that you see here. And what we see here is the groundwater recharge. Sorry, this is in German, but what I can tell you is that these numbers that we have here, or the colors in the Hessian Ried, they tell us that groundwater recharge is about 100, 200, maximum 250 millimeters per year. That is the groundwater recharge in the Hessian Ried. Yeah. And if we now say that we compare that groundwater recharge with the 70 kilograms per hectare of nitrogen excess, and we put these 70 kilograms into the groundwater recharge, we come to the conclusion, and there's a nice equation to do that, that if we would put all that 70 kilograms into the groundwater recharge would have a concentration of nitrate of 300 in this area where we have kind of low groundwater recharge. This area has a higher groundwater recharge, so therefore the nitrogen concentrations in that recharging water would be roughly 100 milligrams per liter. Here in that area we have an intermediate groundwater recharge, there we would have 150 milligrams per liter. Now we are screwed in a way. We have a kind of legal limit, or not a legal limit, it's just a value that we are targeting of 70 kilogram, but worst case would be that then in the recharging water, we would have nitrate concentrations of several hundred milligrams per liter. To recall that, legal limit was 50. Yeah? So this basically would be finish line. You should forget about all these 70 kilograms. You need to go much, much down with that, if this would be the case. Yeah? The farmers tell us already this is almost not working anymore, because then we would not have enough crops on our agricultural land to make the money we need. Yeah? They say this is absolutely bottom line. We cannot take less fertilizer on the fields. Even if this is left over, if we take less, basically the plants will not have enough fertilizer anymore. Yeah. So now we go to the Hessian Ried, and I show you how nitrate concentrations are distributed in the Hessian Ried. Of course, not everywhere we have high nitrate concentrations, but what this shows here that we have some areas where we really have way above 50 milligrams per liter. 50 milligrams is here this red color. This is the legal limit. And in many places we have way above 50 milligrams per liter, and sometimes, and the size of that spots tell you what is the depth of the well, even in 30, 40 meters depth, we have more than 50 milligrams per liter of nitrate. And this is the problem in the Hessian Ried. There are areas where we don't have that, but actually this is enough. We have a large area where we have very high nitrate concentrations in the groundwater. So we can also say now, what is the risk area in the Hessian Ried? Yeah? And this was done actually. It was looked at the Hessian Ried, and it was, we actually did a study on that. Where is risk areas, where we have a higher risk that we have very high nitrate concentrations in the groundwater. If we ask ourselves the question, where is a risk area in the Hessian Ried, we have to take into consideration several points. Yeah? Land use, fertilization intensity, of course, properties and special features of the soil. I will tell you this in a second, why this is so important. Groundwater flow, groundwater vulnerability, of course. Is there a kind of confined or is it unconfined? Characteristic of the aquifer sediments. All this have to be taken into account if we define a risk area for nitrate. Potential solutions for the nitrate. Of course, sustainable solution would be reduce the N surplus by good agricultural practice. We try our very best, or the farmers try their very best. They are very frustrated that we still have that nitrate discussion because they think they do enough. Yeah. However, there is another solution, although this is non-sustainable, and I will tell you later why it's not sustainable. And this is a so-called natural attenuation concept. And actually, this is a very important point. And I will show you why this is an important point. Because nitrate, to some extent, is also degraded by natural processes. Yeah? However, this is not sustainable, and I will also show you why it's not sustainable. Yeah? Natural attenuation, this is a definition of natural attenuation. You also know this from industrial contaminated sites. If people say that these compounds will be degraded by natural processes, then we call this natural attenuation. And it's called variety of physical, chemical, or biological processes that are at work in situ under favorable conditions, acting without human intervention, reduce the mass, toxicity, mobility, volume, or concentration of contaminants. Yeah? This is the definition of natural attenuation. For nitrate, we have also natural attenuation, of course. Yeah? And the first one is assimilation and conversion to biomass. This is what we want, actually. This is what produces our crops, actually. So this takes out the nitrogen and the nitrate out of the soil. We have a second natural attenuation process, which is microbial nitrate reduction. Yeah? And I will show you later what that means and why also this is not sustainable and is not a long-term solution. Yeah? The next natural attenuation is dilution, mixing, diffusion, dispersion, and sorption. There's a discussion on dilution, of course. Is dilution a natural attenuation process? Yeah. By dilution, we decrease concentration. Yes, we go below legal limits, but we do not decrease the mass of a contaminant. Some people say the solution of pollution is dilution. To some extent that is right, and our waterworks basically do exactly this. If they have one well with too high nitrate concentration, another well with low nitrate concentration, they mix the water. They go below a legal limit and they are actually safe. Yeah? And this is, I think this is okay to do that, but this is of course not a long-term solution. Yeah? So microbial nitrate reduction, I will focus on this point now in the next slides, I think. And if we talk about microbial nitrate reduction, then we have to talk about oxidation reduction processes. Yeah? Oxidation reduction, that is what happens basically with nitrate in soils. And what we have in principle, and I think you all have a background somehow in chemistry, oxidation reduction involves the change of oxidation states of reactants. During oxidation reduction reaction, electrons are transferred from one species to another. That's the background. Yeah? Oxidation, deliverance of electrons, reduction, acceptance of electrons. This is basically what we are relying on if we talk about degradation of nitrate in the subsurface. And I will tell you this a little bit more in detail also in the next slides. Yeah, there's an example, cadmium plus iron, cadmium as an ion here, iron is transformed to cadmium now as a solid and iron as a 2+ ion, yeah, basically. And there we have basically the two half reactions in this oxidation reduction reaction. As an example here, one is delivering electrons, the other one is accepting electrons. Yeah, and cadmium accepts the electrons, and iron is delivering the electrons. That are these two half reactions. And then we have basically a sequence of oxidation and reduction reactions. Yeah. And this is basically what we can have. We can have oxygen reduction, denitrification, manganese reduction, iron reduction, sulfate reduction, and fermentation. That are the things we have, and they are always coupled to an oxidation reaction. Yeah? If you have a reduction reaction, you need to have an oxidation reaction. Yeah? And a reduction reaction will proceed with any oxidation reaction that is located at a lower PE. That is a measure basically on the reduction potential here. And that is the origin of the arrow actually here. Yeah? So a reduction of sulfite can work with oxidation of organic matter, but not with the oxidation of iron, because these two are not overlapping. So you need somehow that these basically, that an oxidation reaction has to be located at a lower PE as the reduction reaction. So that is the background of this. In groundwater now, what happens actually, we are going basically, if you go vertically into the groundwater, we will typically go through these different oxidation reduction reactions. Yeah? And if we now have a profile from the top of the groundwater table to the down to the deeper parts, then we go through redox zones. Yeah? And typically, what is the starting point of such redox processes is the infiltration of organic matter into an aquifer. Yeah? If you have organic matter and that is basically percolating into an aquifer, then reactions are starting. And the first reaction that starts basically is consuming oxygen. Yeah? So we have organic matter, and I'll show you later the reaction that is related to that. And then we have oxygen, and then this oxidation reduction reaction goes on. If the oxygen is consumed, nitrate is following. And this is why I discussed this, yeah? Because nitrate can also be degraded in the redox sequence here. After nitrate, there's manganese and iron reduction. These are the products of these reactions. Then there's sulfate reduction, and then we have fermentation. The background is that we go through a sequence, and as long as there is oxygen, we will not degrade the nitrate, is that these microbes get some energy from these reactions. All these reactions are based on microbes. Yeah? And if they use the oxygen in an oxidation reduction reaction, they gain much more energy, and it's minus because they get the energy out of the system. They get much more energy compared to the other reactions here. The second one now is the denitrification. There's a little bit less energy yield. Therefore, the microbes first go for the oxygen. Yeah? If there's no nitrate left, they go for manganese reduction, they go for iron reduction. So if you have manganese 4 reduction, you produce manganese 2 plus. For iron, if you have iron 3 reduction, you produce iron 2 plus, which goes into solution, and then you go to the next steps. Yeah? So the driving force for the microbes is energy yield. Yeah? And the energy yield decreases from here, from the oxygen here to these lower parts in the redox sequence. And these are the reactions that go on. Yeah? First, we take the oxygen, and this basically is the organic matter that is typically present in soils. And if it's present in soils, the bacteria take the oxygen, they produce CO2 and water, and they grow by this, of course. Yeah, they gain energy out of this reaction. Now the oxygen is gone, actually. There's no oxygen left. The bacteria took all the oxygen, and then the next reaction starts. And this is the important reaction for us. Now, if there's still some organic matter present, and in soils we have organic matter, then the bacteria use the nitrate. Yeah, you see that here, now the nitrate is consumed. And they produce, from this reaction, organic matter, that is this, the nitrate. They produce N2, they produce bicarbonate, they produce CO2 and water. Yeah? And also they gain, again, energy out of this. That is the point. If this is done, basically the next steps come, and you can follow these steps here with the different reactions. Now the bacteria change from the nitrate to manganese and iron reduction, basically. And the organic matter, if it's still there, is then going into this reaction and then this reaction. And so on. Next reaction, sulfate reduction. Next reaction, if there's still some iron hydroxides available, there's another reaction going on. Next one is methane is formed. Yeah? And then you have still some organic matter, and then they form methane and CO2. Yeah? And if that is over, then there's another reaction going on. And you see that in this last reaction, you release iron 2 plus. Yeah? So this basically is the sequence of redox reactions you might see in an aquifer. You have that. And we discussed that yesterday a little bit. You have a lot of sites where you have oil spills, for example. Yeah? And in an oil spill, exactly the same occurs. Yeah? If you have an oil spill and you spill that oil to the groundwater and you develop a plume, if you go through that plume, you see all these different redox reactions taking place, because the oil is a hydrocarbon, and the oil somehow is comparable to this here. Yeah? This is basically then the input into the reactions. And therefore, if you have a contaminated site, then you produce right away a plume with all these different microbial reactions going on, from aerobic respiration to the last stage, which is methanogenesis. And this is natural attenuation, actually. So we are looking into this, actually. Yeah? This is what is of interest for us. We have nitrate, which comes from agricultural activities. And we have the upper part of the aquifer. We have now groundwater recharge. Yeah? The water is coming with nitrate in it. Yeah? And if you have still in the water oxygen, yeah, then the nitrate is not touched. Yeah? The nitrate is not degraded. If you have oxygen still available and you have organic matter that you have in the soils, the bacteria consume the oxygen. Only if the oxygen is gone, they could consume the nitrate. Yeah? And we saw the reaction, if they consume the nitrate, we are getting rid of the problem because the nitrate, the N, is converted to N2 and there's a gas and is going to the atmosphere. So we are looking into this reaction here, and we call that from a chemical point of view, heterochemotrophic denitrification. Yeah? Organic matter is the reductant. So we have here that organic matter, we have the nitrate, yeah, and then we have this reaction. I showed that before. It's written in a slightly different form, but it's the same reaction actually. Organic matter, you have the nitrate, the bacteria do basically, with the help of water, form nitrogen gas, bicarbonate and CO2. Yeah. This is the main reaction that was known for a long time, and then there was another reaction identified. Yeah. The bacteria can also do another thing. They can not only use the organic matter to degrade the nitrate, there's a second reaction going on. And this one is called autolithotrophic denitrification. And what they do is they have iron sulfide, pyrite, for example. If that is present in the soils, and we have that in many soils, you have that actually, and in aquifer materials, you also have that. They take this iron sulfide, pyrite here, nitrogen in the form of nitrate and hydrogen, and with this they produce nitrogen gas, sulfate, iron, and water. Yeah, so this is the second reaction that is helping us, yeah, because we put now the nitrate into the soil, it's flushed down to the aquifer through the soil, and we have two natural attenuation reactions going on. Heterochemotrophic denitrification, autolithotrophic denitrification. One takes the organic carbon, the other one takes the iron sulfides. Actually, if you go to the field, you can even measure an increase in sulfide, for example, or bicarbonate, if there is a lot of nitrate put into the ground, and if these reactions are going on. You can see that these two parameters that you can, of course, measure in your water samples are increasing. However, there's another point that is now a very important one. Assuming that we permanently introduce nitrate into the soil and then into the groundwater in the end, then we deplete basically the source of these reactions. We deplete, for example, the pyrite because it's consumed. Yeah? If there's a reaction like this going on, the pyrite is gone. Yeah? And if you put more and more and more nitrate into this ground, pyrite at one point is completely gone. The same for the organic matter, not in the upper part here in the soils, but if you have some organic stuff in the aquifer materials, it is also just consumed and not enriched anymore. So it's just consumed. And this basically is, of course, natural attenuation, what's going on, but it's, of course, not sustainable. If you consumed all the pyrite, if you consumed the organic matter, which is in the deeper part of the soil or in the aquifer, then nitrate goes through like a tracer. It cannot be degraded anymore. And that is the problem that we are facing. Yeah. So if we now talk again about what is a risk area, yeah, and then we see that we have here, we have a settlement, here we have the agricultural parts, and this is the situation we have in the Rhine Valley. This is the so-called Odenwald, that is a mountainous area here. This is the Rhine Valley with all the sediments in here, and this is the Rhine. And then if we now infiltrate nitrate all the time, the nitrate is degraded by the processes I just told you. These two processes degrade nitrate when it's flushed into the aquifers, but it's a resource which is finite. Yeah? And if you put more and more and more nitrate into the ground, you consume all these different reactive species. The organic carbon plus the pyrite is consumed, and then nitrate in a way breaks through, goes to the Rhine, or breaks through and goes also to wells that are used for drinking water purposes. So this is that's the problem of these degradation processes, that they are not sustainable because it's a It's a finite resource that we have here for the degradation of the nitrate available. What we did, we went to the field. And if these two things are gone, actually, then we have only oxygen in the system. We have nitrate in the system, but the oxygen is not consumed anymore because the partners are missing. You can't consume that anymore because you have no organic carbon anymore and you have no pyrite anymore. So then the aquifer stays oxidized. And if the aquifer stays oxidized, that's for sure meaning we do not degrade nitrate anymore because there is no partner for this reaction. The organic matter is gone, the pyrite is gone, and we still have oxygen. If there would be degradation going on, first the oxygen would be consumed and not the nitrate. So we went to the field, and what we did actually, we went to several wells in the Hessian Ried, and we had a sensor here. And the sensor is measuring basically redox potential, it's measuring oxygen basically, and we also took samples, I think it's also measuring online nitrate. Yeah. And then we went to wells which are fully screened, and we lowered the probe into the well, and we monitored how is the oxygen content, the nitrate concentration, and the redox conditions developing in this well, in the water column that you have in the well. And what you see then basically is, in the upper part, in many places you have high nitrate concentrations, 100 milligram per liter here, and then they completely drop to zero. Yeah? In the upper part you have oxygen. Oxygen drops then also to zero. And then we have the redox potential here. We have here a high redox potential. Here we have a low redox potential, a much lower redox potential. And this indicates us that we have here basically a border or a line which separates the oxidizing conditions from the reducing conditions. If we are oxidizing, meaning we have oxygen in the system, nitrate is not consumed. If the oxygen is gone, we go to reducing conditions, then also the nitrate is consumed. Yeah? So you see this jump in conditions, into the jump in redox conditions here, which is also expressed by jumps in oxygen concentrations and a jump in nitrate concentrations. Under oxidized condition, nitrate is stable, will not be degraded. So now let's consider we put nitrate all the time into this aquifer. And if this nitrate reaches this zone here, it's degraded. Yeah? But if it reaches this zone and is degraded, it's depleting the reactive phases, organic matter and pyrite. So in principle, the idea would be that this zone would go down actually over time. Yeah? Because you put more and more nitrate into the system, you consume the reactive species, so that border would move down. And eventually, the water would reach, for example, a well which is used for drinking water purposes. So we went then for something we called Redoxfront Screening. Yeah? And Redoxfront Screening means we took wells which are fully screened and we lowered that sensor down in these wells. And we did that here in this case from 2005 to 2012. And what is indicated here is basically the jump in redox conditions. Above these lines, we have oxidizing conditions. Below the line, we have reducing conditions. These are the measurements, and that is the trend line in the measurements. And that means from the year 2005 to the year 2012, the redox front, so the jump between oxidizing and reducing conditions, came down year by year in some of these wells by 0.4 to 0.3 to 0.4 meters per year. Meaning that this zone was going down 0.3 to 0.4 meters per year because we are putting nitrate on the top. We consume the reduction potential in that layer here, and therefore we generate oxidizing conditions. Yeah? And this is the risk we have if you put more and more nitrate on. In the end, we will have a fully oxidized aquifer, and there's no reduction of nitrate anymore. We wrote a publication here on that for our state agency on this one here, where we analyzed the situation in the Hessian Ried, yeah, and we determined what is the potential in the sediments of the Hessian Ried here to reduce nitrate. Yeah. And what we did actually is we went here to two places. Yeah, this is Darmstadt again, and this is the so-called Escholbrücken place. This is the Jägersburger Wald place. And we drilled cores, yeah, and we took material out of these cores, the soil, out of the sediments, out of the cores, and we analyzed these sediments, yeah. So this basically was analyzed for pyrite, that is the active element that we need, that is degrading the nitrate, and of course for organic carbon, because also this degrades the nitrate, yeah. And then some other measurements we did, yeah. And then we used that samples, the soil samples, for some experiments in the laboratory, yeah. Batch experiments for nitrate degradation, that's what we did. We did also some isotope studies. I will later show that the isotopes are a very nice tool to analyze these degradation processes. For example, the N14 in the nitrate, also the sulfur were analyzed. And you remember that in one of these reactions, sulfate is produced, and you can measure then the isotopes of the sulfur here, and I will show you that in a second. Yeah. What you see here basically now is the Jägersburger Wald core. Yeah, we took a core which is 40 meters. Yeah. And then we measured the organic carbon content, that is this line here in that core, and we measured the pyrite, sulfite, disulfide in the core. And what we saw is that in the upper part, we have very low concentrations of organic carbon and low concentrations of sulfite, disulfide, very low concentrations. And that zone was oxidized. Yeah? So this means already here in that zone, all these phases that would catalyze the degradation of nitrate are gone, actually. Then there was a jump in the concentrations of the sulfide phases here. You see, here it goes up, and also the organic carbon goes up here. And this zone is reduced. Yeah? So here we have potential still present to degrade the nitrate. Yeah? And we see that here in these analysis of the cores very nicely. What I find really impressive is if you look now into the cores, these are the cores, the actual cores from the Hessian Ried. Then you see basically here it's a sand, a fine sand to medium coarse sand. You see that here the colors are kind of light brownish, and then the colors change to grayish. Yeah? And if you go back to this slide, this is exactly the jump between the oxidizing conditions and the reducing conditions. Yeah? So this is the oxidized part of the core at the core, and this is the reduced part of the core. These are the different drilling cores that we have. And you right away see here's the oxidized thing, here's the reduced thing. Here, no degradation of nitrate anymore. We are oxidizing, so nitrate is not degraded. In the deeper part of the core, we are reducing, and you see that in the colors here, that you have here reducing conditions, and here nitrate is reduced. Very interesting. Now we went into the laboratory with samples, and we had these two drillings. This is the Escherbrücken drilling, and you see here TOC concentrations here and sulfide concentrations here, and we took a sample out of this area here. Almost no organic carbon, almost no disulfide concentrations. This material was basically from here, from an area like this. We took another sample from Jägersburger Wald, and it's exactly from this area here where we have high TOC and high sulfide concentrations. So this sample came from that part of the borings, from the reduced part of the borings. And then we went to the laboratory and we did batch experiments. This is the material, there's water on top and there's nitrate in it. And we started these laboratory experiments with a concentration of 100 milligrams per liter of nitrate. This is the Jägersburger Wald sample. And what you see in the Jägersburger Wald sample is the nitrate is degraded over some tens of days, but it's degraded in the N20. In the Escherbrücken sample, nothing is happening, no degradation at all. And if we go back, we see this is the Escherbrücken sample. There are bacteria, of course, in the batch experiment, but they can't initiate the reactions because there's no organic carbon or very low organic carbon, there's no sulfide. In this case, the bacteria have these two things that they need to degrade the nitrate, and therefore we see the degradation of the nitrate. Very interesting. So this is basically the observation in the laboratory, that actually no degradation here in that sample from the oxidized area of the aquifer, and very good degradation of nitrate in the reduced part of the aquifer. We also did measure basically the isotopes in the nitrate. And I'm not so sure how familiar you are with isotopes. If you measure isotopes, for example, in a compound like nitrate, and that nitrate is degraded, then bacteria typically first degrade the nitrate with the lighter isotopes in it. Yeah? That means the remaining nitrate is enriched in heavy nitrogen isotopes. And this is what we actually see here. Yeah? This is again the Jägersburger Wald sample. This is nothing degraded, 100% degraded. And this is the isotopes in the nitrate. And if you go more positive, that means the nitrate, the nitrogen isotopes in the nitrate gets heavier. And you see this trend here in the degradation, the nitrate gets heavier, the remaining nitrate gets heavier in the nitrogen isotopes. A clear indication of a microbial degradation process. In the Escher-Brücken sample, nothing happens. There's no degradation, so no movement on this side. Also, no enrichment in the isotopes, of course, because nothing is degraded. And you can also plot that versus the nitrogen in the air, but it shows the same picture. Yeah? So if you degrade it, you see an isotope effect. Very nice. In principle, you can prove that these microbial reactions are going on. Yeah? Second thing here, in these experiments that we measured is the sulfate concentration. Oh, there's a T missing, sorry. We measured the sulfate concentrations. And what you see here basically is in the Jägersburger Wald sample, the sulfate is going up. Yeah? In the Escher-Brücken sample, nothing happens. And what we see here basically, that also this reaction is going on. Not only the organic carbon is reactive, here we see exactly this reaction. Pyrite, there is pyrite in the Jägersburger Wald sample. And then the pyrite, with the help of bacteria, reacts with the nitrogen, the nitrate here, and it produces sulfate. And the sulfate in our experiment goes up. Yeah? So we prove also that this reaction is going on in our experiment. Yeah? This is a kind of complicated thing. We also measured now the sulfate isotopes. What we saw basically is this is the natural sulfate isotopic composition in the Jägersburger Wald. And this is the isotopic composition of the sulfite that is produced from the degradation reaction. And what we saw is that here from the sulfate we measure in the water samples, also in the field, go down actually and go to a composition which is more close to the sulfite which is produced from the oxidation. That is the native sulfite in the water. And in the course of the experiment, the sulfite isotopic composition changes, of course, to this direction. We also see that basically in the field, actually, this is the sulfate background because there is sulfate already in the samples, in the water samples. But this is the sulfate we get from the oxidation of the nitrate. And in our experiments, all data that we used for the isotopes are in between somehow. And in the field, we saw the same thing. We don't have the background concentration of sulfate. As soon as the reactions are starting, the sulfate moves into this direction because we have the degradation of the nitrate. We later did also a column experiment. Also, this was an interesting exercise. You have a column here, and the column is filled with the material from one of the drillings. Yeah? And then we have basically a pump sending here nitrate water into this column, and then and we pumped here nitrate-containing water in, and we monitored what happens with the nitrate between the inflow and the outflow. Yeah? I just show you data from inflow and outflow. Yeah? And what we assumed is, okay, there is some reduction potential here, so the nitrate is degraded in the column. And I'll show you now what comes out here. It's a very messy presentation here, a slide, but I explain it to you. What we see here actually is the nitrate. This color is the nitrate, yeah? And we send the nitrate into the column. And after one pore volume, the nitrate comes out here at the upper part, yeah? It comes out here. Then it stays somehow constant. This is also very normal for such an experiment. The bacteria now are adapting to that situation that they now have nitrate. Then basically the nitrate is decreasing, nitrate is degrading, and then it's degrading basically to zero, yeah? When it starts to degrade, we see that sulfate is forming. Yeah? in the outflow, we have more sulfate compared to the inflow. This is the inflow sulfate. And then in the outflow, we have much more sulfate. That means we have the reaction that we just discussed happening because there's sulfate production. Nitrate stays basically here at very low concentrations, but then sulfate concentrations go down. This means we are having consumed all the pyrite, and these reactions cannot be maintained anymore. And then the nitrate concentrations go up again. It goes up, goes up, goes up, and then it's basically at the point close to the inflow concentration. So here we exhausted all the reduction potential. So here we start this autotrophic denitrification, that is this here. Nitrate is degraded with the help of the pyrite, and we produce sulfate. And you see that here. Nitrate goes down, sulfate goes up. Then we have here the highest reduction kinetics, but then this basically is exhausted. There's no more pyrite. So also the sulfate goes back to normal concentrations in the end. And we have then a change to the heterotrophic denitrification, because the sulfate is not produced anymore, but we still have degradation. That means that we have this reaction going on now. And in the end, basically it's exhausted and no reaction anymore because all the reduction potential in the sediments is exhausted. So this completely matches what we expected. We have reduction, but the reduction potential is limited. And in the end, the concentration of nitrate goes up, then the whole column is oxidized, actually. So initially, autotrophic denitrification followed by heterotrophic denitrification until the reduction capacity is exhausted. I have one more slide, which is also a little bit complicated, but I'll try to explain it. You can also, in the field, now measure how is the nitrate degraded. And there is a very interesting method, which is called the N2 excess method. And I try to explain it here in this slide here. What we have, if you take a water sample out of an aquifer, then you have in that water dissolved gases. And we are focusing on two gases here. And the gas we are focusing is nitrogen and argon. And in the atmosphere, we have a fixed ratio between nitrogen gas and argon gas. So also in groundwater samples, you find that fixed value between nitrogen gas and argon gas. And you can measure that in our laboratory with a gas chromatograph. If you now take a water sample, you can analyze the ratio between nitrogen gas and argon gas. And in some cases, what you will find is that the ratio is not fitting anymore with the atmospheric composition. You have much more nitrogen in the sample, in the water sample, dissolved nitrogen gas, as you would expect. Where could this come from? The excess of the nitrogen gas, the N2 gas, can only come from these two reactions again. And that means if you degrade nitrate, you produce N2, and that changes the ratio between the nitrogen gas and the argon that you typically have in an aquifer. I hope that was kind of clear, because it's a very interesting finding that we have now, because now we can go to our aquifer and go to wells and take a sample. And we took in this case a sample from here, a sample from here, and a sample from here. And then we measured basically nitrogen, nitrate, and we measured the ratio here to come up with this N2 excess. And what we measured up here is that we have a lot of nitrate in the water sample and a little bit of nitrogen excess, because the reactions were going on. Here we have a lot of nitrate and no nitrogen excess, meaning there's not much reaction going on this flow path here. And in the deeper part, we did not measure any nitrate. So there's no nitrate. You would say this is a part of the aquifer where we would have never seen nitrate. However, you have a huge amount of excess of nitrogen gas. And that is due to the fact that on the flow path, basically, the nitrate is degraded and you are enriched in this nitrogen gas that you can measure as an excess. And now you can go to basically groundwater modeling, and you can come to the conclusion basically that here in this area, if you do flow modeling, you know that this is the area that brings the water to that part of the well. You can see that in principle here was an average of 71 milligrams per liter of nitrate infiltrated, degraded, and now you have that excess of nitrogen gas. Yeah? And you can calculate back that the water initially had nitrate, but you can't measure it anymore because it's degraded. The flow path here is 20 to 53 years. Also, that comes from modeling. So the nitrate that was put in here was applied something between 20 and 53 years prior to today. Yeah? And then it traveled through the aquifer and it reaches this point. You don't find the nitrate anymore. Everything is degraded. And 100% is degraded. In this case, almost nothing is degraded. Just 2% is degraded because you have that little excess. And here you can back calculate that 17% is degraded. You still have nitrate and 17% is degraded that you see in the nitrogen excess. Yeah? This will be important also in a second, and I'm close to the finish line now here. Now, what you can already see here, if you have here an agricultural area, that is the important point now for the conclusion, and you have basically here fertilizers applied, yeah, then you would see an effect of a change in agricultural practices at this specific spot only in 20 to 50 years. Yeah, this is the modeling that brings us that number. But it means there's a huge delay between a measure that you do here, not applying fertilizer anymore, and the effect that you might see in a well. And this now goes back to the court case for Germany and the European Union. Yeah? We have monitoring wells that are located basically not exactly where the nitrate is basically put on the fields, but some distance down gradient. And in this case, this well will show an effect of a measure you do on the surface somehow only years later. So it doesn't matter what you do right now up here, this will not change anything here because the water takes so long time to come to this point. And some people say Germany was not very clever in selecting the wells for that monitoring network of nitrate, because in the first 20, 30 years, you basically will not see anything because you have that groundwater flow. We did a calculation here now for the Hessian Ried. And the Hessian Ried basically has a kind of thick unsaturated zone sometimes. And also this time has to be considered. So you have now agricultural measures on the surface. You apply a fertilizer. You have groundwater recharge. That fertilizer goes down. At one point reaches the groundwater table. Then it's transported and at one point reaches now the well, which is sampled, and the results are reported to Brussels. This map shows you from the Hessian Ried just the time, how long does it take for nitrate to go from the surface to the groundwater table. Yeah? And then you would have still the travel in the groundwater to the well you are sampling. And we have places in the Hessian Ried where already the passage of the unsaturated zone takes more than 15 years. So if you do something here in agriculture to improve the situation, it will take 15 years before you see it at the groundwater table, and it will take another 10, 20 years before you see it somewhere in a well. And that is one of the major parts of this. Yeah? For some monitoring wells that we have basically in the Water Framework Directive, and we report the data to the EU, it will take decades before we see a measure at the surface showing up in a well that is monitored. That is one of the problems we have. Of course, there's too much fertilizers applied, but this is one of the major problems, that a measure is not reflected in a well after a short time period. It takes a long time. And this makes farmers very frustrated, I have to say. They do something, but it's not showing up. What did we do in order to solve that situation? We now implemented monitoring stations in fields. This is a field site, and we implemented a monitoring station here. You see, we dig a hole. This is a kind of, you can go down there now, and we implemented all types of sensors now, and I will show you a slide in a second where you see these sensors. We have here a monitoring station for the groundwater also. This is Lice, you might remember him. We saw him yesterday. I'm not sure whether he is here today. He was involved in all these studies here. So we implemented that monitoring station, and that monitoring station measures now right away below these fields nitrate concentrations, oxygen, redox potential, all the different things. Many parameters are measured. So we think, and this is something we know now, because we have already a lot of data, that we can now monitor what changes here in the unsaturated zone if you change agricultural practices very early. Yeah, if the farmer does something different here, we will see that immediately down here. Well, I should not say immediately. It will also take some months because the water that is applied here has to reach our sensors. But we have a better measure on whether a measure of the farmer is successful or not. And this is now discussed with our ministry, whether measuring stations like this will be implemented in more places. We have just one now. We could show that's a very good tool to prove that a measure of a farmer has an effect for the deeper parts here. And we would like to implement these monitoring stations in other places in the Hessian Ried. Yeah, I think that's it. I don't want to go to the uranium. That would be another story. Sorry, I go back here. Okay, that's it. I hope you enjoyed my talk and understood everything I said. Sometimes it's a little bit complicated if you are not in that topic, but I hope the main points came across quite clearly.
No, thank you very much. So interested, very excellent information about this problem.
Yeah.
Thank you very much. Everyone's happy to have to participate in this lectures and presentation, and hopefully we have you next month, maybe March, beginning of March.
March, yes.
Yeah.
Just let me know. I can suggest you other topics if you are interested, and then we can do this again.
Very, very interested topic that you have chosen them, and we have you in next month. After the finals finished, students, they finished their finals.
We stay in contact.
Thank you again for your preparation, for everything, supporting, for very, very good, very excellent lectures and information that you have presented them. Thank you very much.
Have a good day.
Bye-bye. Have a nice day.
Bye-bye.
See you soon. Bye.
Thank you.
Bye-bye.
Same for you.